Hello students, welcome. Before you read this problem, the problem which was asked in the examination of engineering mechanics of University of Pune in 2015, before we read that, I would just like to, tell you that just brush up what we have, the work energy principle, the equation which we do. The basic thing is that suppose you have a object which is say here, this is the object here, and this object is, let's say, moved here, right? Okay, and there is a spring attached to both the objects. Now what we want to so this is position 1 and this is position 2. So what we do is we write an energy equation for the object when it is at position 1 and 2, and we are saying that it's basically law of conservation of energy. We are saying that this object when it is at position 1 will have spring energy, which is given by half k1 x square. It will have some potential energy, right? If this is your datum, it would have some, if this is the height h1 and this height, let's say, is h2, right? Then we say that at position 1 it will have some potential energy at position 1. It will have this might have a velocity v1, this will have velocity at position 2, the same object will have velocity v2. Then the kinetic energy will be half m v1 square. This is at position 1. Plus maybe there is some force acting somewhere like this on this object F, and because of this force and this distance which the object is moving from 1 to 2 is say d, then the work done on this object because of this force will be F into d. This is also energy supplied to object. Okay, so object when it is at position 1 has three first terms: spring energy, potential energy, kinetic energy, plus if there is force acting, external force acting on the object and it is acting throughout the displacement d, then F into d will be the energy supplied to the object. But while it is moving, maybe there is some frictional force, like frictional force will act like this, and I am denoting it as F suffix r. So frictional force will eat away the energy of the object 1 because it is opposing its motion. So I am writing this as minus Fr into d. Okay, so this is the energy which the block will have when it reaches point 2, and this energy will be in the form of again it will have kinetic it will have spring energy. So let's say spring energy, it will say it is half k2 is the stiffness of spring, x2 is the compression or elongation, or in general we can say it's the deformation, right, or compression or stretching. This is the spring energy, plus it will have mgh2 as potential energy, and plus it can have half m v2 square, right? So this is the general expression we will use, and we are always writing this general expression, right? So remember this. Fine. Now let's read the problem. Now I'm just removing this I'm removing this diagram, but I'll retain the equation. You know, this is the most general expression of law of conservation of energy, or you can say work energy principle. And now see, this equation we are going to use in any problem. And now look at this problem. What is the problem? There is a bullet which is moving at a speed of 300 meters per second. Has its speed reduced to 270 meters per second. There is some, it's not neatly written. A bullet moving at speed of 300 meters per second has its speed reduced, it should be reduced to 270 meters per second when it passes through a board. So board, that means some object with some thickness, the bullet is moving through it, and when it moves through it, its velocity reduces to 270 meters per second. Determine how many such boards the bullet will penetrate before it stops, right? So let us make that sketch. So this is the let's make a board, and this is the thickness of board. Let's say T. This is the thickness. This is the bullet which is entering the board and it is coming out. Okay. When it enters the board, its velocity is 300 meters per second. When it leaves the board, it is 270 meters per second. Now, what you are asked is how many boards we require. So that the velocity when it is emerges out is 0. Because when it stops, penetrates, so determine how many such boards the bullet will penetrate before it stops. That means the final velocity should be not 270, but it should be 0. That means you have to add many more such boards. Okay, you have to add many more such boards. Now see, what we can do is this. We know the situation about one board. Now why the velocity is dropping from 300 to 270? Obviously it is dropping because of frictional energy, right? Now let's look at this equation which we have written. Look at this equation. Now apply this equation here. If we apply the equation here, we will say that is there a spring to this bullet? No, there is no spring shown here. The bullet has only kinetic energy. So, and please note that the bullet, it's not told that the initial height of bullet and final height is not mentioned. So the bullet is, we can say it's moving straight. That means in this equation, the equation which I am showing here, this equation, the blue lined equation, here the spring is not there, so we can remove this. Similarly, height difference H1 and H2, that is not there. So potential energy of this bullet, the bullet is entering at the same level, leaving at the same level. Why do you say so? Because it's not mentioned, right? There is no reference to height and etc. So we can say that potential energy on both the sides is same, right? So what you ultimately are left with is half mv1 square plus F into D. Now look at this. What is F into D? If you remember, is there any external force acting on the bullet? No, there is no external force acting on the bullet. There is not shown any external force. So F into D, that is also gone, right? So what you have is half, this equation reduces to half mv1 square minus Fr into D, right? So I'll just clean this. Minus Fr into D is equal to half mv2 square, right? So this is our equation. And what is this Fr into D? This is energy lost, or not lost, energy eaten away by the frictional force. Okay. Now what you can find out in this equation is this Fr into D. We can find out Fr into D, right? So what is this D? The D is essentially this thickness, because the bullet is entering here and coming out here. So you find this D is essentially the thickness. So we can find out now, let's find out Fr into D, right? So you can say Fr, if I take Fr into this, I can write it like this: half m1 v1 square minus half m v2 square, right? This is equal to, right? This is equal to Fr into D, right? This is equal to Fr into D. So we can say this is equal to Fr into D, right? Now that means essentially the drop in kinetic energy, is equal to the change is equal to the energy spent in overcoming the friction. Okay, so this is what we have now. But we don't want this to be we don't want the bullet to be emerging at 270. We want bullet to be emerging out at 0 meters per second. That means it's not enough to just have one board, but we should have many such boards. And we want to find out how many boards you will have to attach, so that the bullet, when it is coming out, will have energy equal to it will have velocity equal to 0. That means kinetic energy will be 0, right? So what we do now, let us add more boards. So let's say we don't know how many boards. I'll just say I'll add some boards. It should be of the same thickness. Right? So let's say we have added so many of the same thickness, okay, although it might not look, but the same thickness. And when it comes out, now velocity equal to 0, right? Let's say we are adding n such board, right? We are adding n such board. Now, if you are adding n such boards, obviously the frictional energy now will be spent will be n into Fr into d. This is Fr into d is for one board. So the frictional energy now will be n into Fr into d, right? So we can write now the same equation, similar equation for this situation. So what is this situation? First equation we'll write, this is point 1, position 1, this is position 2. At position 1, the bullet, actually the bullet is, it's coming out and it's not moving ahead, but because it has 0 velocity, it will just drop down, right? At this point, this is the point at which velocity will be 0, remember. Okay, so we'll write this equation, again the same energy equation. Now we will write, it is half m v1 square, v1 is 300, right? Minus 0, why? Because v2 now is 0, okay? Is equal to n into Fr into d, right? So we have these two equations, please note. We have these two equations, and in these equations, we know v1, we know v2, right? Then we have also known, please note, we have also known value of Fr into d. Now Fr into d, this value will be, if we calculate that, this value will be, from this equation we should find out. So from this equation, right, you get Fr into d, you can check this, will be equal to 8550 m, because there will be m also, right? So I am writing this from this equation. Please note, this is this equation, one and the same, this or this, right? Fr is equal to, now once you have this, you can write it here, substitute this value in equation 2. Substitute this value in equation 2. So you will write half m v1 square is 300 square is equal to n, and into Fr into d we have written that this is the 8550 m, right? So m gets cancelled, right? And from both sides, and you will find the value of n equal to 5.26 boards, which we can say is equal to 6 boards. So when you have 6 boards, the bullet will have 0 velocity. Okay, thank you.